Okay, so now we're going to be talking about carbohydrates and glycoproteins. Okay, so monosaccharides are going to be your simplest carbohydrates. Has everybody heard that before? Okay. You guys have had like a health class sort of thing? Okay, so did they tell you should eat lots of carbohydrates? Do you need to eat grains? That's a lie. You need absolutely 0 grains in your diet.
Yeah, it's the one thing you actually do not need to eat.
Anyways, we'll go into it. So carbohydrates, these are going to be carbon-based molecules that are high in hydroxyl groups. The empirical formula for carbohydrates is this right here. That is CH2O, and that's to some number. So for example, if there's a 1 here, it'd be CH2O, right? 2 here, C2H4O2. Everybody got that okay? Okay, that's empirical formula. These can have additional groups or modifications to them. We've seen some examples of this, like ribonucleic acid, deoxyribose, that sort of stuff, right? These can have better described as polyhydroxyaldehydes and ketones and their derivatives. You'll see that we'll divide the carbohydrates into aldehydes and ketones later. And so a great definition of them is polyhydroxyaldehyde or a polyhydroxyketone. Okay? Poly meaning many hydroxyl groups, right? Okay. Monosaccharides are going to be aldehydes or ketones that will contain 2 or more hydroxyl groups. The smallest monosaccharides are going to be composed of 3 carbons. The monosaccharides exist in many isomeric forms. Everybody remembers isomers? Isomeric meaning different isomers, right? Okay. Does everybody remember your projections from last semester? Have you guys still been using that a bit? Okay. We'll kind of cover it again a little bit, but yeah. If you need more review, let me know, okay? Monosaccharides, mono meaning 1, right? Saccharide meaning it's a mere, right, repeating unit. So monosaccharides are going to be carbohydrates that are 3 to 7 carbons in length. They're also usually called simple sugars. Here's some different examples of our monosaccharides. You will note that there is a biological version of the names, and then there's a chemical version of the name, right? The chemical version of the name being very similar either to historical common naming or being very similar to the new IUPAC naming, depending on when it was discovered and became a thing. Okay. So right here we see the dihydroxyacetone, literally acetone with 2 hydroxy groups on it. You see that okay? Fantastic. This is actually a ketose. Why is it called a ketose? What's that group? Ketone. And this is a sugar, so ose. Yeah, monosaccharides, ose. Okay. Right here we have an aldose. Why is an aldose? Aldehyde, ose. Yeah, aldose. Does anybody have any questions about this? Again, this is the classification, ketone or aldehyde, ketose, aldose. This would be the specific sugar's name. What's the difference here with D and L? Anybody tell me? Why is this D and L? You got it. They're isomers, right? Or specifically, this is the DL as in the chiral. Remember when we swapped the chiral groups? The one coming out at you and the one going in? Yeah, that's what we're doing here, aren't we? We're swapping chirality. The monosaccharide nomenclature. So nomenclature can be based on the carbon chain length. 3 carbons will be trioses, meaning 3, obviously. 4 carbons will be tetroses. 5 carbons are pentoses. Yeah. 6 carbons are hexoses. 7 are heptoses. We give up at that point. Theoretically, you could have more, but that would not be a simple monosaccharide, right? Nomenclature, this is also based on the identity of the most oxidized group. The most oxidized group being the keto group for ketose, or aldehyde group for aldose. Isomers, these are going to be constitutional isomers, molecules with identical molecular formulas that differ in how the atoms are ordered. These are just the definitions from organic chemistry, in case you're wondering. It's the review. These are stereoisomers, are going to be molecules that differ in spatial arrangement, but do not in their bonding order. We can have either D or L configurations for these different sugars. Monosaccharides, these can be enantiomers, which would be mirror images of each other, or diisomers, which are not mirror images of each other, but are still stereoisomers of each other. The number that are possible is 2 to the n power, where n is the number of asymmetric carbon atoms. Everybody remembers asymmetric carbon atoms? Okay. That's like the chiral carbon atoms, right? Okay, this right here is actually a nice flow chart that sort of gives you the whole thing in one glance, okay? And I would go ahead and go through this a few times and just make sure you understand it, okay? I'm just going to quickly go through it here. So we have isomers. These have the same molecular formula but different structures. We have constitutional isomers, i.e. their constitution is different, right? So we have a complete rearrangement of bonds but the same overall formula, okay? And so this is glyceraldehyde. Yes, glycerol, the one you probably know really well and have seen a lot in your other biology classes. Yeah. Okay, so on the other hand, we have stereoisomers, right? And so stereoisomers will be the atoms are connected in the same order, but they're going to differ in spatial arrangement. So you're not going to have this double bonded carbonyl group here. This is not going to be in a different location, right? It's going to be in the same location. You'll have a hydroxy group on the same carbon. It just is going to be flipped, right? Okay, so spatial arrangement is the only difference. These can be subdivided into enantiomers or diisomers. Enantiomers are going to be non-superimposable mirror images. We did a lot with that before. And so these are non-superimposable mirror images, right? They're a mirror image, but we cannot superimpose them like our hands. Okay, and we have D and L there. We have diisomers. So these are going to be isomers, but they're not mirror images. Okay, and remember that usually happens where you flip like two groups. You flip one, right? You don't flip both. Okay, and so we're seeing that right here. See how we flipped one group and we didn't flip others? So they're not mirror images. Okay, and then those can be further subdivided into epimers. This is going to differ at the several asymmetric carbon atoms, so we're going to have that several times. And then we have anomers, and these are going to be isomers that differ at a new asymmetric carbon atom formed on the ring closure. These are going to be 90-something% of the time in your body what the monomers, what the monosaccharides look like. Okay, so your sugars are going to look like this 99% of the time. Right? They ring open every now and then. I think I actually mentioned that back in last semester. Anyways, you all have a wonderful weekend. I will see you on Monday. And we will, I should probably finish this chapter or come pretty close. Did everybody see that I messed around with your Google Classroom class schedule? So it's a bit more according to what I'm actually covering, when I'm covering it. Okay. Did anybody actually get onto the YouTube and try that? Okay.